Welcome to the deep dive. Today we're looking into something pretty interesting, a new way of figuring out how strong bamboo reinforced concrete beams actually are.
Yeah, we've got this research paper, Bomfemetlai, 2025. It lays out a simplified model for this.
Right, and our mission really is to understand why bamboo, why consider it instead of steel, and how does this model help predict if it'll work without getting totally lost in the technical jargon.
Exactly, because fundamentally bamboo just doesn't bond as well with concrete compared to steel. That's the core challenge.
Engineers usually use those really complex computer simulations, right? Finite element analysis.
They do, and it's powerful, but it takes a ton of computing time and resources. So this new model, it's aiming for a simpler path, a shortcut, maybe.
Okay, a shortcut. And it's called lumped damage mechanics. Is that the term?
That's the one, lump damage mechanics, or LDM. And, it's not totally new. The idea has been around.
Oh, where else have they used it?
Well, it originally came out of seismic analysis, actually, looking at how conventional steel-reinforced concrete buildings react during earthquakes. So they're taking that established idea and extending it now to bamboo.
Huh. Okay, so how does lumping the damage help with bamboo concrete specifically?
Well, think of it like this. Instead of meticulously tracking every single tiny crack, which is what those complex simulations try to do.
Right, that sounds intensive.
It is. So LDM sort of zooms out. It focuses the damage, the cracking, into specific zones, usually at the ends of a beam element, like hinges that get looser as the beam bends and cracks.
Okay, so concentrated damage points.
Exactly. And it uses this concept called the strain equivalence hypothesis. Basically, you look at the damaged material and figure out an effective stress that would cause the same strain in an undamaged version of that material.
I see, so you're comparing damage to undamaged.
You got it. And importantly, for this model, they're not considering any yielding or permanent bending in the bamboo itself. It's focused on the concrete cracking.
So the damage is all lumped into these hinge-like spots representing the cracking.
Precisely. The model uses something called a flexibility matrix. It's just a mathematical way to describe how bendy the beam section is. And this matrix includes both the normal elastic bending and the extra bending caused by the cracking damage.
And what makes the cracks, well, crack more?
They call them damage-driving moments. Essentially, as the bending moment, the force trying to bend the beam increases, it drives the damage, the cracking, to progress further.
Okay, but bamboo concrete isn't the same as steel concrete, so the model has to account for that difference somehow.
Ah, yes, that's a really crucial adaptation here. They developed a specific cracking resistance function just for bamboo reinforced concrete. It's different from the one you'd use for steel.
How's it different?
It basically captures that bamboo concrete tends to be, well, more deformable before it fails. It has higher ductility, you could say.
More bendy before it breaks.
Sort of, yeah. The function has a term for the initial cracking resistance, how much force it takes to start the first crack. Then there's another part related to how the bamboo adds resistance as damage increases. And there's this exponential term, too.
Exponential. Sounds complicated.
It sounds it, but it's key for capturing that extra ductility, that ability to deform more, which is characteristic of these bamboo beams compared to steel ones.
And is there a point where it just gives up a maximum damage?
Yes, there's an ultimate damage value, let's call it due. That represents the point where the model predicts failure, usually linked to the bamboo slipping significantly within the concrete.
Okay, theory is one thing. Did they test this? Does it match reality?
They did. They validated it against actual lab experiments. One set was from Mondal et al. They tested beams with different amounts of bamboo, like 1.5%, 2.5%, 3.7% reinforcement.
And how did the model do?
Pretty well, actually. Using just two simple finite elements, basically just dividing the beam into two chunks for the simulation. The model's predictions for load capacity and failure points were quite close to the experimental results. The ultimate damage value was around 0.89.
Just two elements. That sounds computationally cheap.
Exactly. That's the whole point. Way less demanding than traditional methods.
Did they check against other experiments too, just to be sure?
Yep. They used another set of data from Molly and Data. Different beam dimensions, different reinforcement ratio, about 3.8%. Again, they used just two elements.
And results? Similar story.
Broadly, yes. The model matched the overall shape of the experimental load displacement curve quite well. The numerical failure happened just a tiny bit later than in the actual test, but still a good fit. The ultimate damage was, again, very close, 0.8899.
So the big takeaway seems to be this simplified LDM approach gives a good enough picture of how these bamboo beams behave, but without needing a supercomputer.
That's the essence of it, yeah. It's computationally efficient. It makes analyzing these kinds of structures much more practical for everyday engineering design or for doing reliability studies where you need to run many simulations.
And we should just remember that simplification we mentioned earlier, it doesn't really model the bamboo itself deforming plastically, does it?
Correct. That's a current limitation, mainly because there isn't a lot of data on bamboo's behavior under cyclic loading, like back and forth bending. So they simplified that part out for now. Keeps the model usable.
Right. Okay, so wrapping up this deep dive then, we've looked at this novel, simplified model using lumped damage mechanics. It seems like a really promising way to analyze bamboo reinforced concrete beams.
It captures their unique cracking behavior, that extra ductility we talked about, without needing massive computational effort.
And for you, listener, this really highlights how engineers are getting creative with sustainable materials like bamboo. They're not just saying, let's use bamboo. They're developing the smart tools needed to use it safely and effectively.
Absolutely. It's about adapting to resource limits and environmental needs.
Which leads us to a final thought to leave you with. This model works by lumping complex behavior into a simpler form. Where else in the world of sustainable construction materials, think rammed earth, maybe other natural fibers, could similar, simplified lumped models help us understand them better and encourage wider use?
Hmm, that's a good question. Something to chew on.
Definitely. Thanks for joining us for this deep dive.